Okay, hi everyone. We're going to get started now. So thank you all so much for coming. My name is Allie and I'm one of the co-directors of Science in the News. Can you raise your hand if this is your first Science in the News event? Welcome. So to everyone else, thanks for coming back again. So Science in the News is a graduate student group that has two goals. The first is we want to make science accessible and bring it to the general public. And our second goal is we want to train graduate student scientists how to communicate their science more effectively. And we do that through a bunch of different ways, including this seminar series, which we have these nice flyers for if you want to grab on your way out. It advertises the rest of our program, which will be going until November 28th. We also have a bunch of other events, including a science cafe, a really prolific blog, a day-long conference in the summer, as well as a podcast. So if you're interested in kind of learning about science and talking to scientists in a different formats, you can check out our website to see our schedule of events. So tonight we have Lily and Judith, and they're going to be speaking about designing AI-enabled technology for society. Their talk will be broken up into a few different parts, and we ask you to hold your questions until they get to their specified question break. About halfway through, we'll have a short intermission where you can go use the restroom, grab some snacks. And then at the very end, they're going to have a short demo. So if you'd like to participate in the demo, please come down to the front of the lecture hall, and it will be all set up on this table. So, and then one last reminder is we really do appreciate audience feedback. So on your way out, if you wouldn't mind filling out our feedback form, we really take your suggestions seriously and actually use your suggestions to choose the topics for our seminar. So if there's something you really want to learn about or want to see, just write it down and we'll try to include it in the next round of events. So with that, we'll let our speakers get started.
Hi, I'm Lily, so I'm a third-year PhD student in computer science, and I do research in designing hardware and computer systems for machine learning and artificial intelligence, which you'll hear more about today. And to start off.
Yeah, so I'm Judith. I'm also a third-year PhD student working in a similar area as Lily. And today we're going to be talking about how we design AI-enabled technology and how that relates to us as users and society. So some of the questions that we're going to be answering or asking in particular are, how do people interact with artificial intelligence or AI? How does the technology around us enable AI? So in terms of technology around us, we're used to interacting with phones, with watches, with laptops, things like Amazon Alexa or Google Home devices, automobiles, and also the cloud. And how is AI enabled on each of those platforms? We'll also talk about what impact these AI-enabled devices have on us as users, and finally, how looking into the future these devices are changing in order to support more and more applications of artificial intelligence. So the talk will be separated into three sections. We'll start off with a bit of a background on what is AI and why we care about it. Section 2 is going to talk about understanding computing at different scales. And in particular, we're going to focus on mobile devices like our cell phones and also these data centers. For the purposes of this talk, data centers are just going to be this cluster of computers that could be thousands or tens of thousands of computers. If you think about this like hooking up 10,000 of your laptops together, that's going to be considered a data center. But we'll get into some of the specifics of the scale later in the talk. And then in section 3, we'll go over some of the future challenges in supporting AI on other devices going forward. So before we really get into the computing at different scales, let's define what we mean by AI and some of these buzzwords that we might have heard in the news or just around us, including artificial intelligence, machine learning, and deep learning. So the way that we're going to define AI is through an example. So most people have probably at least heard of Netflix. typically what happens when we go on Netflix is we go on Netflix, we try to browse for a show, and Netflix itself suggests a lot of shows to us. So in this case, I logged into Netflix, and Netflix told me to watch Stranger Things. And the question is, well, how did Netflix know that I wanted to watch Stranger Things? Or how did Netflix know to suggest Stranger Things to me as a show? And so the first term here, artificial intelligence, is the ability for a system to perform these seemingly cognitive tasks that we're used to. So in this case, Netflix is suggesting a show to us that we usually attribute to a friend telling us, or a coworker, or a family member telling us. The fact that a computer system is able to do this is amazing, and that's what we consider as artificial intelligence, this cognitive ability. So the next question then is, well, how does Netflix know how to suggest these shows to us? How is it performing this process? And at a high level, what's happening is on Netflix and similar types of streaming services like Amazon and Hulu and HBO Go, is they're tracking some information about users on the global scale. So not only the United States, but North America, South America, overseas, everywhere. And they're logging information like, what shows do people watch? What are people liking? If somebody likes a show such as Stranger Things, what other shows did they watch before that? What shows did they watch after it? Did they like those shows? Did they not like those shows? And with this process, streaming services like Netflix are able to learn patterns and what shows or movies people are interested in watching. And the process of learning from this large data set is what we call machine learning. So machine learning is a process of taking data that we collected from somewhere and learning patterns within that data. And so when we talk about machine learning, there's typically two steps to machine learning, or any machine learning process. There's what we call training and inference. Training is a process of taking data that we've collected and learning these relationships or learning these patterns. So in the case of streaming services, this would be the data that we've collected from the global scale and are learning what shows people want to watch and what they're interested in. And then when we log on to these streaming services, Netflix is telling us what show we should watch next. It's deploying that learned process or those learned patterns to us. And that deployment is called inference. And so when we think about interacting with AI on a day-to-day basis, this is the part that we're more used to. It's the deployment or the actual use case or the application of the learned method or the learned patterns in data. And for the purposes of this talk, we're going to be focusing on inference or deploying these machine learning models. So machine learning, we said, is a process of learning patterns within data sets. One important type of technique that people have started to use in order to learn these patterns is called deep learning. And deep learning is really powerful because it allows designers to provide the system, which we've shown over here. We'll get into a little bit more detail in the next slides. It allows designers to provide some data set or some data set like these labels that we've seen before, and the process automatically learns these patterns on its own. So you don't need some computer scientist to sit there and program all of these patterns manually. And that's why deep learning is so powerful. So let's take a closer look at how some of these deep learning systems work. So a word that's synonymous with deep learning is neural networks, which you might have also seen in some articles or just as buzzwords thrown around. Over here, we're taking the example of image recognition. So we want to provide this neural network an image of a dog, and we want it to somehow automatically classify this image as being a dog. We want to provide it some image, and it'll tell us what it is. What is it a picture of? We can represent neural networks as a series of layers. So over here we have 4 layers. And each layer is going to take this input image that we have, in this case the picture of the dog, and apply some sort of functions on top. And by applying these successive functions, at some point the network has looked at. The network has deciphered that this is a picture of a dog. So how do these layers in particular work? So for instance, the first layer might just simply be tracing the edge of this image. So we take the image of the dog, we trace it, and this is the outline of what looks like a dog. Not this particular dog, but yeah. The next layers try to build higher level features, or in this case, they're recognizing that this dog has a cute nose, or this picture has a cute nose and fluffy ears. These are things that we associate with dogs and other animals. And so after the first and the second layer over here have seen these noses and the ears, they can then recognize that this is actually a picture of the dog. And this is how typical neural networks and deep learning is used today. So why do we really care about deep learning? Why is it so important? One of the big reasons here is deep learning is being deployed for a bunch of different applications. So in terms of image recognition and processing, we're seeing deep learning in applications like Face ID. So if you use your iPhone, you take a picture of yourself and it automatically unlocks the phone, that's Face ID. That's using a neural network or deep learning in the background. Tagging photos, if you upload a picture to Facebook and it automatically figures out who is in the picture and tags the people in the picture, that's also using these neural networks. Photo captioning. You give it a picture and it generates a description of your picture for you. Reverse image search. If you've gone to Google and you provide them an image, they automatically tell you other images that are similar to the one that you provided. In terms of natural language processing, we're starting to see deep learning being used for speech recognition. So if you think about Siri or Amazon Alexa, when you talk to these devices, they need to take your spoken speech and transcribe it into text so that can be understood. That's also based on deep learning. Translation, when systems are automatically translating text from English to French, or French to Chinese, or German to English. Speech synthesis, when systems like Siri and Amazon Alexa speak to us, we want them to sound as human as possible. And that requires some form of machine learning, and in this case, deep learning as well. So why are we only hearing about deep learning now? Like, why is this such a big phenomenon today? And the cycle over here really boils down to what makes deep learning possible. And the two pillars over here are computing power and big data. And so in order to make deep learning possible, we need a lot of computational power. We also need a ton of data in order to train the models that we're talking about. And so a good analogy that a professor at Stanford came up with is some of these deep learning systems are like a rocket. where the model or the neural network is the rocket ship, and the fuel represents big data and this computational power. So in order to shoot this rocket up to the moon or to Mars or wherever, we need a lot of fuel. We need a lot of data. We need a lot of compute power. So where is the compute power and this data coming from? So let's just take a case of image classification so you can think about this as Face ID on your iPhones. In terms of compute power, training one of these neural networks that we've been talking about 15 years ago would have taken a year's worth of compute time. So you would sit on what would have been a computer 15 years ago, and it would take you a year to train even one of these networks. Today, this process takes a mere hours. So you can actually train like a couple of different networks in a given day. In terms of data, in order to train one of these networks, it takes 1.2 million images. Just think about it. There's somebody in the background or a bunch of companies in the background that have taken 1.2 million images and actually labeled what each of those images are. They know this image is of a dog, this is of a house, this is of a chimney. We're only starting to see these sort of large-scale data sets forming in the past five-ish years. And neural networks themselves take hundreds of millions of parameters or values to be stored. And so our modern phones and laptops and desktop computers that we're used to are only starting to reach the point where you can actually store these on our phones and our mobile devices locally. Let's dive a little bit deeper into some of the computational advantages that have been seen in the past 15 years. So these are just some cell phones from 20 years ago and then cell phones today. And already you can see that 20 years ago we were used to thinking about cell phones as something that did that were used for mostly calling people and texting maybe. And today we are used to these cell phones having screens, doing all these sort of applications, doing Snapchat, doing Facebook. And so from 1990 up until today, we've seen phones become much, much more powerful. So today our phones can have up to 256 gigabytes of storage. That corresponds to about 12 million pages of text. If you had books, that would be 12 million pages of books. These phones run at 2.4 gigahertz. You can think about that as doing 2.4 billion operations or adds and multiplies in a given second. Comparing this to 50 years ago, this is what computers used to look like. So this is one of the first computers, the ENIAC, that was designed in 1946. It weighed 27 tons. It took up probably the size of this room that we're in right now. It was used for mostly doing what we associate with calculators today in terms of adding numbers together, multiplying numbers together. We'll have a demo later, but these were programmed using punch cards. It was a very manual process, whereas today you don't really see that. And in comparison to the 2.4 billion operations per second, the ENIAC did 5,000 operations a second. So in comparison, our phones today are 500,000 times faster than one of the first computers. They're 200,000 times smaller, and they fit in the palm of your hand or in your pocket. So the other driving force for enabling deep learning today is this notion of having a lot of data, or what we call big data. Now, where is this data coming from? So let's just think about the amount of data that gets produced in any given minute across the globe. So in 1 minute, we have about 2.4 million Google searches, 46,000 different Instagram posts, 450,000 Twitter posts, 18 million weather channel queries, 4.1 million YouTube views, 300 new Facebook profiles, 156 million emails, and 103 million spam emails. And all of this data is being used to train some of the new deep learning networks and neural networks that we're seeing today, training these artificial intelligence systems. In addition to all of this data being collected, we also have data coming from the voice-enabled devices, so Siri, Google Home, and Amazon Alexa. Sensors across our homes, so our refrigerators today have temperature sensors. They have sensors for a whole slew of things. We have sensors in our thermostats. We're uploading personal images, video, and audio everywhere. We're also collecting data from devices like Fitbit for tracking how many steps people walk or how much exercise people are doing. And so just to recap over here, deep learning is really being driven by some of the advances from the computer systems and also being able to collect all this new data. And what we're going to be focusing on for the remainder of this talk is how AI is being used across devices around us. So on mobile phones, on smartwatches, laptops, Google Home type devices, and also in the cloud, and how these devices are changing going forward. Any questions so far? Yeah, in the front.
In talking about the big data, you did mention all that's gathered from cookies, and retail processing, and all these other schemes, which I seem to think might even be more than what you mentioned.
Yeah, so the question was, in the big data side, we did mention data being collected from cookies and retail processing. That's true. That slide didn't enumerate all the different sources of data that are being collected. That was just supposed to be a snapshot of some of the data that is.
Yeah, so the previous slide where you showed in 1 minute with the one before, yeah, where it shows like in 1 minute all this data is gathered.
Yes.
This is all proprietary data. Does it mean that only big companies with access to this proprietary data make advancement in deep learning?
So the question was, all of the data that's been mentioned over here is proprietary, and does that mean that only big companies can make advancements?
Yeah.
So it is the case that a lot of the data that is being collected is proprietary by some of the big companies, but we're also seeing these companies make public data sets that are available to researchers and academics and other smaller companies, let's say. And that's really been one of the driving forces as well, being able to share some of the resources and some of the data sets. So the 1.2 million images that we're talking about over here was from a public data set. I'm going to start handing off to it.
A little involved. Great, thanks, Vivian. So the next thing we're going to dive into is a couple of concrete examples of how you personally might interact with a bunch of different neural networks specifically, but in general, AI-powered applications every day. And so 2 specific examples that we'll go through are what really happens when you ask Siri a question on the back end, and then also what really happens when you type something into Google, sort of unmasking what's really going on, and in doing so, try to understand how computing differs and how the design of different devices changes at different scales and for different types of devices. But in order to understand that, first I'm going to talk a little bit more about what are all these devices that we want to support and be able to deploy artificial intelligence on directly to support these specific computations. So these range all the way from the biggest scale of computing, which, as we already mentioned, is a data center. And for the purpose of today's talks, you can think of as just rows and rows of thousands and thousands of machines, all working, communicating with each other to do coordinated computations at an enormous scale. But this actually ranges all the way down to a smart device on your wrist, or in the air as a drone, or in your kitchen as a fridge. Really all scales of devices that we interact with, whether or not we realize it. That includes Google Home type devices as well. But really the question that we're left with as system designers is what actually makes these devices different? So every different scale of computing has different design constraints, basically. So for the purpose of today's talk, we can just isolate sort of the lowest and highest level that you might encounter, which is when you think about a smartwatch or your mobile phone, the top constraint is the battery. We know that cell phone batteries die more quickly than we'd like every day. And what we think about is that these AI applications can cause a huge drain on the battery. But then there are also other constraints, both in terms of completing computations on your cell phone or in the cloud, which is the speed at which those computations complete. And then there's also the constraint of the physical size of the device. And then one more constraint that we'll talk a little bit more about later is the ability or the need to send data between different devices. So the main constraint here is if you need to be, for example, connected to Wi-Fi or cellular data in order to send, for instance, an image from your cell phone to the cloud for storage, or a simpler communication bound where if you have a smart watch or another household device with very limited storage, it's a small device so it can't hold very much data, you rely on something like a Bluetooth connection to be able to send that data to another device, like your phone or your iPad or your laptop, what have you. So these constraints all become really important when we think about any single example of interacting with a device. So whether it's a voice command or whether it's typing in a Google search, and those are the exact 2 examples that we're going to talk about today. So first, I'll dive a little bit deeper about how you encounter artificial intelligence when you interact with a mobile phone, with or without realizing it. And the first of these is an example close to my heart, animated emojis. And the reason why I want to talk a little bit about this is because there are actually several different components that utilize artificial intelligence to make this fairly silly task happen. So not only is there a neural network employed in order to filter an image, but there's also additional processing required and additional machine learning techniques to do things like object detection and object tracking. So actually looking at where your face is within your camera lens and then tracking it as you make different silly faces so that it can be mapped onto the emoji face. A lot of computation goes into even something as trivial as this. And then another very important example is in understanding language semantics and in actually doing translation on your mobile phone. So this is another task that requires a ton of computation, and that is being enabled by deep learning, specifically these neural networks. So the example that I'll talk about in a little more detail is when you ask a voice command to an intelligent personal assistant. So there are a lot of different names for different intelligent personal assistants. Most major tech companies have their own proposal. You have your Siris, you have your Google Assistants, Alexa, Cortana. I don't want to set off any devices, but I did want to just show you that there's a breadth of different proposals for voice assistants, that these are popping up in application-specific areas and in general on devices, and just so that interacting with devices with your voice is sort of the next push in AI-enabled technology in general. And it's a very important task for us to be able to support. And obviously, there are a lot of different interactions that you can have with an intelligent personal assistant. It can be quite convenient, and as speech recognition gets more and more effective on your mobile phone, it will become more convenient, hopefully. So what I want to do now is I just want to do a bit of a walkthrough of what happens when you ask Siri a question. So one question that I ask pretty often is, hey Siri, what time is my alarm set for in the morning? Because usually I change it thereafter. But the idea is that I'll ask Siri this question and I'll get a response maybe a couple seconds later. There'll be some delay. And what actually goes on in those 2 seconds? Well, the first thing that needs to happen is Siri needs to detect that I said something at all. So Siri will have one dedicated neural network that's just latently listening and waiting to detect whether I have initiated a command. And other personal assistants have that key command, like the Hey Google, that triggers in the same way. So that's one instance of artificial intelligence in this cycle. But then Siri actually has to do speech recognition to translate from a spoken word to the actual command that I intend for them to execute, which is what time is my alarm set for the morning. But just this text transcription is often not enough. And there's actually a third step that uses AI in order to understand the transcribed command, to go from a sentence in English to actually what Siri needs to do in terms of interacting with the mobile device. So in this case, Siri has quite a bit of work to do. She has to open the clock application and retrieve data from that, from inside that application information. But it's worth noting that there are a lot of other tasks that Siri might need to complete during this cycle, including communication with the cloud if you ask her to search for something online, for instance, so that there can actually be quite a bit of work in this step of acting on the command, which may or may not use artificial intelligence as well. In this simple example, but there's actually another instance where another neural network is required, which is to generate the response back to me, to generate natural sounding speech back to me. And I think this life cycle is interesting, mostly because there are distinct tasks that Siri needs to complete that use artificial intelligence in different ways, and the latency, the time it takes for her to actually respond back to me needs to be minimal for me to not have Siri get on my nerves. So there are really a few considerations in terms of designing a system to support Siri. Well, we want to be able to do all of these complicated computations on my device, so on the computing power that fits in my pocket, instead of having to, for instance, send my speech to the data center and process it there and send a response back. So in terms of responsiveness, we really want to be able to do these computations on the phone, but there are two big issues with this. The first of which is that transcribing, so taking speech and turning it into text, transcribing just 1 second of spoken words requires 1 million operations. And as we saw, that's just one part of the larger cycle of what needs to happen in order to create a response. And the takeaway message here is that AI drains your battery, but what we know is that we're going to want to do these exact set of computations over and over again, very frequently. And we're left with the question of, if we want to do AI-related computations very frequently, we need to be able to do them efficiently in order to avoid the battery drain and in order to be able to avoid sending any data to the data center and back. So the solution that is being actively proposed and just snuck into the iPhoneX is that when we have an application, so in this case, neural networks specifically, that we want to execute over and over again, many times a day, we can actually build hardware specifically tuned to do just that thing. And that will make it more efficient in terms of the energy and the time it takes to complete this task. So to sort of understand why this is the specific approach we take as system designers, to sort of just build a separate thing that does one task, I'd like to introduce a task that I do every day, which is toast bread in the morning. I know this is something that I'm going to do every morning, very frequently, and it turns out I do have something in my kitchen that can heat up my bread for me, and it's the oven. So what I could do every morning is I could put my toast in the oven, and I could wait for the oven to heat up, and I could, do other things in the kitchen. That's fine. But what I realized is that for a relatively small task of toasting bread, the oven is great at doing a lot of different things, but I only need it to do this one thing, and I want it to do it every day. So right now, I'm using a appliance that is far too large and takes far too much time and energy relative to the task I want to complete very frequently. So enter the specialized hardware, which is my toaster. And this is the key concept for why there's so much interest and development in a specialized hardware component at different scales to support artificial intelligence. And this sort of gets to the crux of a lot of the work that Udit and I do as part of our PhDs. So the analogy that I'm drawing here to make it more concrete is that the oven is effectively a traditional processor. It's what we would call a CPU. It can do many different things. It's an effective machine. But since I know I want to do one specific task very efficiently, very frequently, what I do is I build a specific unit that just does that thing. And Apple calls this the neural processing unit. You can find it in the iPhone X. And for AI-related computations, you have 9 times faster computations, and you use 10 times less battery for the same tasks. So this is really, really key. And I just wanted to take a moment to point out that this is actually representative of a more general trend of what's going on inside your smartphone. So this is a picture that I find really cool. So this is actually a photo of the main processing chip, computer chip, inside of an iPhone 8. So this came out in 2017. And what I'd just like to point out, well, first, I'd actually like to point out the scale of this. So pretty much all the computation of your cell phone is done using this device right here, and the size of this device is smaller than a dime. Pretty crazy. And what I'd like to point out is that the general purpose processing, the CPU or the oven of the chip, is basically this portion right here labeled CPU. And there are other more general processing elements. For instance, this processes graphics or certain image tasks. And a lot of this is dedicated to memory, storing data. But what I'd actually like to point out is all of these little white outlined blocks. Those are toasters, basically. They are specially designed hardware components that each do just one task. And hardware designers at Apple, and this is a trend across many different companies, have noticed that the phone overall operates much more efficiently if you identify the key tasks that are done. So a lot of these are supporting directly or indirectly artificial intelligence, or something like video streaming, other common tasks that are becoming more common on mobile phones. But each one of these blocks does one specific task and does it efficiently, and that conserves battery and time overall when you're using your cell phone. And what I'm showing here is that the number of these specialized blocks that are included in a given mobile phone, so this is the different iPhones from the iPhone 4 in 2010 all the way up to the iPhone 8 in 2017, the number of special toasters in that chip has been steadily increasing, which is sort of good news for the kind of work that Udit and I do. We're done. So I want to briefly, we're going to take a brief break right now before we talk about another example of how you interact with artificial intelligence. But any other questions?
Just a quick question. So you mentioned that the NPUs are really good at like matrix multiplication, linear algebra stuff.
Yeah.
And I know that GPUs are also exceptionally good at that. Like Amazon Web Services has their own GPU units. So do you see Amazon basically having some sort of NPU type cloud-based computing system, or is that something that you would anticipate being relegated to kind of these more isolated cases?
Yeah, so GPUs are good at matrix multiplication. The NPU is actually even more specialized than that. It's specialized for the different patterns of how data moves for neural networks, which is why I can do it even faster. But we're actually, the next example we're going to talk about is going to get into cloud scale support for artificial intelligence. So maybe we'll follow up with you later.
Hi. So like you mentioned about like how AIs can recognize like faces or like text, but like can it like actually create something that like less predictable? For example, like if I like feed the data, feed like the AIs with something like bunch of like data about music, can it create like the entire new music? Or like if I feed it a bunch of like dance new, can it like create the entire new dance new?
So the music example, I actually do know. Oh, repeat the question. I'm sorry. So the previous question was about use of GPUs for neural network computations as well, and what the implications are for doing things at cloud scale instead of the mobile devices. And the question I just got was about how these machine learning methods might apply to less concrete data forms. So instead of images or text, something like music. Is that your question?
Yeah. And also, how do they create a new like entire new music or entire new like? Yeah.
And also, so the follow-up was, can these types of methods also create new content, new music? So they're actually these are active areas of machine learning research. There are examples of neural networks that can fed music, can produce other music. That is actually an example called WaveNet from Google. But I think in general, those are the kinds of tasks, and there are actually different kinds of models called generative models that might address that question.
Hi, so you mentioned that most of these devices are consistently listening to the command, so A go or AC. So this is a major privacy implication. How is there any move towards, let's say when someone's house, I don't want to be recalled.
Right.
I know I'm not being recorded. Is there any way that you just say stop for maybe the next 2 hours, next 3 hours? Like, you don't do any of this.
Yeah, so
the only way I can think of it, Google device, there's a switch on it.
Yeah.
And otherwise you just snap that power.
Yeah. Yeah, so the always listening feature is usually something you can turn on and off, but in general, I do think that data privacy and security with these devices is like the top challenge moving forward, and that's actually going to be the basis of third-party talk.
Okay. So I'll follow up that is, so most of the audio record on phone, is that data siloed or is it shared with other apps? Because other apps can access your data that's on your phone. What about audio recordings? Are they completely siloed and encrypted, or are they just stored as it is?
That I actually don't know specifically,
Yeah.
but that's an interesting question, because you're right, data access between apps is kind of wild west.
Yeah, so the Android system. So.
Okay, thank you.
Yeah, so we're going to take a short intermission now for about 5 minutes. So feel free to grab some snacks and then be back here soon. Thanks, guys.
I've heard the word, I don't know. Sounds like someone. Right, yeah, so you have your own method, but I mean, are you looking for like a specific algorithm or how to compute the probability at the end instead of the yes, no? Unfortunately, Yeah, we're not well versed enough in like any emphasis at the end. I would say that similar problems. Yeah, it's nice to meet you. Yeah, thanks for coming. Yeah, that was. Oh, that's what you guys went on. Yeah. So this. Yeah. It's pretty similar to
So that's when you out what things going on.
Yeah. That is cool. But who's first? I guess I go on first.
Why?
That would be.
it has CPU and it. Like you can kind of see just the scale, like this little CPU that's a fraction of that chip. It's like you probably do all of that. Like a time frame. Yeah, this is all sockets. We just add the iPhone. Yeah, it sounds good.
Sorry, what?
Yeah, so this is how you send it.
I don't like that.
Yeah, and then this is
Okay, I think we're going to get started again. So just as a reminder, if you are interested in participating in the demo, please come down to the front of the lecture hall at the end of the talk. And also, I remind you to fill out our feedback form on your way out. Thanks, everyone.
So in the previous part of the talk, we really was talking about AI on mobile devices, particularly intelligent personal assistants that are closer to what we're used to interacting with. Now we're going to shift gears to a completely different type of system, namely a data center, and how we interact with these massive scale computers and how AI is run on those computers as well. So in order to study how data centers work and how AI is run in some of these systems, we're going to be taking the example of online search. So when you go onto Google and you submit some sort of search query, how are those requests processed and how is content returned back to you? And these data centers, we'll get into what these look like on the next slide, but they're used for a lot of different use cases as well, or a lot of different applications, including large-scale data analytics or scientific computing, and many other things. But we're going to be focusing on these search requests for the purpose of this talk. So these are some facts that we thought were pretty interesting to think about, especially in terms of how big some of these computers or some of these data centers can get. So earlier we said that you can think about a single data center as a collection of thousands or tens of thousands of computers. The number of searches that any one of these data centers is processing could be 3.5 billion searches per day, or 40,000 per second across the entire globe. And that's just a staggering amount of things that the data center needs to compute. Like you submit 40,000 different requests, and within a second, it needs to return 40,000 different pages, ranking all of the articles across the web and serving the content. We'll get into how some of that works in a little bit. But if you're looking at a single Google data center that has these thousands of computers, how do we actually power some of these clusters? And so in the Netherlands, there's one of these data centers, and typically when we're building data centers, we hook them up to a power plant or like a solar panel plant or something, some large source of power. In this case, I hooked it up to an entire wind farm, and this generates 62 megawatts of power. And when we're thinking about this, we couldn't really fathom how big 62 megawatts was, so we looked up how much power an average home takes up, and 62 megawatts comes to about 50,000 homes. So you can think about a single data center being powered with the equivalent of 50,000 homes worth of electricity. Each of these data centers has up to 10,000 miles of computer cable that are just connecting each one of the systems together. In 2016, these days, in Google at least, these data centers had up to 2.5 million servers, and there's tens of these servers, these data centers across the entire world. So each one of them has tens of hundreds of thousands of these computers. But the real question here then becomes, well, how does a search engine process so many requests per second and serve them so fast? So there's a trade-off between being able to process any one request from one of us as fast as possible so we don't see the delay, but also being able to process requests from thousands of people across the globe. And that's the scale of problems that these data centers have to solve. And so this is just one example of how Google search would work. Over here, we're searching Oprah, and we just wanted to learn a little bit more about Oprah. And when we searched Oprah, we found the search engine returned a list of different articles that are ranked based on what's relevant to what we might be interested in, as well as some information about Oprah as a person, where she is from, when she was born, things like that. Some other videos that might be relevant, and also some other articles or ads that might be relevant. So just in this one page, you can see AI being used in a lot of different use cases. So the first is understanding the request of Oprah and returning some information about the person. And so this boils down to understanding some of our requests or doing some of the natural language understanding that Lily was also talking about earlier. Then ranking the articles to return, that requires artificial intelligence as well. How does the search engine know that we'd be most interested in the first article versus the 10th article? That's all based on artificial intelligence. And then also returning some of these videos that might be interesting to us. Somewhere in the background, we are taking the search query of Oprah and understanding what that means and returning related content. So just to boil this down a little bit further, what happens as we submit one query to a search engine like Google? So this is us. We submit a query, Oprah in this case, that gets communicated to the data center. As communication, if you're on your laptop, could be through Wi-Fi. If you're on your phone, it could be through 3G networks, 4G networks, or whatever. And it goes from your laptop to some router in the building, and then some other base station, like cell base station in Boston or Massachusetts. And then it'll get sent to the nearest data center, which will, in this case, be on the East Coast. I think it's in New York, I'm pretty sure. The next step is to take the query that we submitted to the data center, and then the data center then processes that. And in terms of processing, it's ranking all of the requests, it's looking at related content, related videos. And then the final step is, also in terms of processing, you're seeing some of these tasks being done, like ranking the search requests, building context, coordinating across all of the different machines in the data set. And then the final step is returning the results back to the user, or back to us. And this is done once again through our 4G networks or through Wi-Fi, however you're connected. And so if we start taking a time span of where all the time is going when we submit this request, it takes about 0.1 seconds if we're connected to a 4G network on our cell phone to send the request from us to the data center. So that's 100 milliseconds. And in order to do all this processing, it takes about 0.4 milliseconds, 400 milliseconds. And then returning once again takes about another 0.1 milliseconds. The part that we're most concerned about is this compute within the data center. This is where all the AI is being run. So within 400 milliseconds, the search engine is able to rank all of our requests, understand the context of Oprah, return some related content, return some videos, things like that. And so the question becomes, how is this really done? Like, how is that scale of compute managed at the data center scale? And so in order to understand this, we're going to go back to the analogy that I believe was going on in terms of toasting bread. So before, we were talking about using either a larger oven to toast bread that's very flexible. You can bake in here, you can make cake, you can make pies or toast bread. Or you can use this neural processing unit inside our phones, or particularly the iPhone, that is specialized in toasting bread. But if you see here, another trade-off is this oven can toast maybe 10 or 20 pieces of bread at a time. And this neural processing unit can only do 2 pieces of bread at a time. But we said that for a search engine, we want to be able to do both. We want to be able to process one query as fast as possible, but we also want to be able to process a batch or a bulk of queries as fast as possible. So we want to bridge the gap between these two. And so how do we do this? Enter the toaster oven. And so the toaster oven is a bit more specialized than our oven, a bit less specialized than our toaster, with the added benefit that it can do, instead of doing 1 or 2 pieces of toast from the toaster, it can do maybe 4, maybe 8, depending on the size of our toaster oven and the size of the bread that we have. And so if we actually look at some of the hardware in these data centers, our oven looks like our traditional processor, or what we call CPUs. We've already talked about the toaster, and this toaster oven in the middle is this new piece of hardware that's being developed called a tensor processing, or a TPU. So what is this TPU? So this picture on the right, or the left, is of a GPU that Google has developed in 2016. The interesting thing over here is the white or silver part in the middle is actually just a heat sink. So one of the problems when you develop new hardware that runs really, really fast is the actual chip is very hot. You want to cool it down. So a lot of the real estate to the actual chip that we have is just on cooling down the piece of hardware. The interesting part here is Google, that even though we think about Google as a software company, they're actually starting to get into developing hardware. So as computer systems designers and researchers, this is a really exciting time. This project in particular was a multi-year effort by hundreds of engineers that was released in 2016, and since 2016 they've had a couple different versions of the TPU come out. And this picture down here is connecting a bunch of these TPUs together in the data center. So each one of these purple racks you see is a stack of 4 or 8 TPUs, and they're getting connected to TPUs down the rack and also across different racks. The blue stuff you see over here are just wires. So comparing this to a traditional processor CPU that we're used to, or the oven that we're talking about, the TPU is 86 times faster per unit of power. And this is the type of technology that's really enabling being able to service so many search requests at a given time, 40,000 search requests in a given second, as fast as possible. Now, we've been talking about these different pieces of hardware in terms of toasters and toaster ovens and ovens. How does it actually translate into some of the software and the hardware that is being run on our systems? So in order to understand that, let's just go through how a traditional processor, or the oven that we've been talking about, works. So our traditional processor has 4 different stages. And the first stage is reading some program or a set of instructions from memory. So when you think about programmers writing down code, they're writing this piece of code that's shown over here, and the processor at some point is going to fetch it from its memory. And that's the thing that's going to run. So when you open up your Facebook app, the processor realizes, or our phone realizes that, okay, I need to go find this program called Facebook and read it and do whatever it tells me to do. So after we've read it from memory, the phone then has to decode all the instructions. So it has to understand that the first instruction is multiplying 2 operations, or multiplying A and B together. Then add X and Y, subtract X and Y, and divide C. And that's really the step at which the processor or folks are understanding the type of computations that need to be done for each of the applications on our phone or on the data center, wherever. The next stage is actually performing those computations. So you can think about this as a calculate step, where we take both of our numbers together, and in this case, we're multiplying them. The final stage is writing the results out to memory. And that's really important because that's what we see as users at the end. So when we read a file or we open a file at the very end, that's the output of this entire process. So if you really think about it, the really important parts that we care about in terms of users of technology are only these two stages. We only care about the actual computations, and we only care about the actual result. We don't care about how these instructions or this program is fetched from memory and how it's decoded. That's all extra stuff that's being done. And so when we talk about going from ovens to toasters, that's the real difference, where we don't need all of this extra information and how to run this program. So when we build specialized hardware, we are taking away these two stages. We take away fetching instructions from memory and decoding these instructions or decoding these programs. What we give up by doing this is our traditional processors were very, very flexible. They could do any type of computation we gave them. An oven could bake a cake, a pie, or whatever we gave it. Once you get rid of these two stages, we need to hard code the computations that are actually being done. So hard code what two numbers need to get added together or multiplied together. And that's what makes this specialized hardware much more efficient. If you actually look at the amount of time or the amount of power being spent, there's only a fraction of the time and power being spent on the actual computations. Most of it is being spent on doing these extra work. The other benefit of minimizing this extra work is our hardware becomes a lot simpler now. All we have to do is do the compute stage and write the results back to memory. And these two stages are much smaller now. And because of that, we can replicate them many, many, many times. So this is kind of what happens. We just take the same piece of compute and then write back the results to memory. And we just replicate that piece of hardware, in this case, 12 times. In practice, you'll replicate it hundreds or thousands of times in your piece of hardware. And this is both what the neural processing unit in your iPhones are doing, and also these TPUs at the data center store are doing. They're just taking this very primitive compute and write back to memory operation and replicating it many times. And by doing so, you can run many operations at the same time or in parallel. This makes the overall computation much, much faster. And so far, we've been talking about AI on the edge and also AI in the data centers. The next part of this talk is going to be talking about how we design technology and devices going forward for newer applications of artificial intelligence, newer applications that are coming about. So before we get to that, are there any questions?
So you know how like the Google AIs like rank the result? So is it like, does it have any biases based on like what like the result being ranked? For example, like Wikipedia is like more preferable than like some random blog online? Or like does it like depends on like how the person that search it online? So like this person like search this a lot, and then the Google decide like this sources like is suitable for this person, and then they keep like giving that person the same like result.
So the question was, when we're talking about artificial intelligence as the search engine, how does the search engine rank more popular pages like Wikipedia versus some other blogs that aren't as popular? How does it personalize these results? So I'm not entirely sure how the algorithms work in the back end, but there's definitely a lot of work being done on how, what pages to serve specific people. And so if you frequently go to Wikipedia, your search requests are probably going to start looking at Wikipedia more and more often. So if you go to a particular website, they'll probably start serving you that content more often. And they do this both for one user and also across many different users. Is that
Follow up on his question. Could you elaborate a little bit on Alexa rank?
So the question was, can I elaborate on Alexa rank? What do you mean by Alexa rank?
So part of his question was, how does Google figure out if your search result is personalized to you, and also whether or not a web page is sharp, is credible, basically, or popular. And there's one part of it is done through a page ranking, which is now Alexa rank, but the other one is more so personalized through cookies. But I was wondering if you could elaborate on Google's page rank, which
Great. So the question was, can I elaborate on how some of these searches are ranked, particularly this algorithm that was designed earlier called PageRank, and how that balances just ranking pages and also personalized content. I'm actually not too familiar with how PageRank works and how the modern versions of PageRank are. Yeah, that would be interesting.
I just wanted to quickly follow up about your PageRank question, just to clarify that PageRank is an algorithm from the 90s when Google's first formed in its purest form, and that it's not artificial intelligence. And a lot of what we're talking about is how artificial intelligence has supplemented and in some cases supplanted some of those original algorithms, particularly in how ads are served and related content is identified. That is your question. But yeah, as Udit already mentioned, the last part of this talk is going to be more of an open-ended discussion about future challenges and the sort of most prominent future challenge that system designers are running head into, and which has become really apparent to people both in academia and in industry, is data privacy and security when you're talking about the use, the fair use and the secure use of personal data in a whole host of applications. And so we'll just touch upon some of the design decisions that really matter going forward, and how are we going to responsibly build future systems. So I'd be remiss if I didn't talk, if we didn't address a little bit more of the breadth of AI applications, since we have discussed a lot of mobile-specific applications that you interact with, just that there are solutions for human parity, so equal to human translation in many different languages, and that there's other language processing tasks, and then sort of the fun one that you might hear about in the news is that different AI systems are beating human experts at strategic games. So this is a picture of AlphaGo, which is now an entity acquired by Google. And then also you may have heard of IB Watson, who performed on Jeopardy, but nowadays is working on more serious matters, not the Jeopardy series. But Watson is now being applied for a host of different healthcare applications and financial applications as well, including market predictions, and then in the medical field, specifically diagnoses from imaging. And there are other prominent uses of AI in medical fields that require being trained on sensitive patient data. So that's a particularly poignant place where the security and the privacy of data use is really important. And so that's why we just wanted to talk a little bit about why the biggest challenge facing system designers right now is how to handle, communicate, and store data securely, and to do all of these exciting applications in a way that is fair to the user. So I'll just flash a few examples, but we can think about what we've heard about in the news of most major tech companies coming under scrutiny for either fair data use or hacking issues about data storage and data access through different profiles. So these are the kinds of issues that system designers need to think about. And I just want to spend a minute on why this is particularly important when we think about using personal data for medical applications. Because AI for healthcare absolutely has a huge potential to help people and save lives, but working with that kind of sensitive data comes with a lot of responsibility and also ethical concerns in terms of proper use of the means with which you are using patient data, considering the commercialization of some of these attempts, as well as how data is shared between different applications, different companies, different open source entities as well, and secure data storage here too. And this is already something that's come up in a couple different high-profile cases in terms of determining what the fair use of patient data is, particularly when interfacing with commercial enterprises, like things like startups that are applying these deep learning algorithms to customized drug delivery, things like that. Medical imaging as well is a popular one. So the question we're left with is, in light of all this responsibility, how do we build systems responsibly but still efficiently? So one way to increase security would be to absolutely minimize communication between devices, but we can have a great advantage by being able to send data and leverage the compute resources and the collective knowledge that's available when we do computation in the data center, as opposed to on a local device. So that's just one example of a trade-off of how we decide whether to execute programs and store data locally on devices with or without network connectivity, or offload computing to the data center and make more intelligent decisions in the data center about how that is done. And I should also mention that a lot of this work is driven by development at the software level too, and at the operating system level, and it requires communication and interfacing between people who design hardware and people who design software in order to make effective solutions. But just for the context of today's talk, we can think about the constraints and the properties of different scales of computing. So our local, our handheld devices do have some advantages. They still have an enormous amount of computing power, and if we can reduce network connectivity, that's an immediate win in terms of privacy. But obviously there's limited storage and limited compute, while the cloud as an entity does not necessarily have those restraints, but it introduces a host of possible privacy issues, and it requires communication, so that there are definite downsides to involving computing at that scale. So just to summarize, we want to emphasize that this sort of cycle of as new and better machine learning algorithms come out, or as we identify different applications that require a lot of computing power, this cycle will continue in terms increased computing power and more efficient hardware, and more data being generated, driving the development of new devices. And that new systems are inherently reliant on hybrid solutions that understand different scales of computing, and that you interact with AI every day. So thank you. And as Valerie mentioned, if you stay after the talk, we'll have a bit of a demo up front where basically we've ripped open a couple iPhones so we can point out what's going on in there, and we have some old processors from the 70s and 80s to give you an idea of how things have changed. Any questions?
I have one. So think about devices like Fitbits that are collecting health information, but they ultimately want to like sell me something. That data isn't really being used necessarily to improve my health. And I wonder how companies like that could, or are they partnering with like research or companies that are more focused on actually providing healthcare as opposed to like a commercial entity? If you could speak to like that discrepancy.
Sure. Yeah. So the question was about taking a device like Fitbit where you're collecting health data, but Fitbit is a company with commercial interests. So are there opportunities for collaborating with academics and trying to reap some benefit for humanity and not just Fitbit from that data? Is that the gist? Yeah, so I think that's actually a really good question, and one that gets at a lot of the efforts to develop open source data sets that can be shared. That's particularly hard to do with health data because, I mean, there's a lot of software work for how to anonymize data and things like that. But I think that's the exact kind of direction we'll start to see. It's trying to leverage the data that exists because of these devices.
There's also a lot of consortiums forming, not only between academics and industry, but also different companies or companies and hospitals, and we're going to be able to share that data privately and securely, especially in the case of healthcare. But that's being done for also just images, speech, searches.
Consortiums to improve the quality of translation is very popular area as well.
What are some of the challenges or limitations that hardware engineers face with coming up with like specific chips that do specific things? Because if they're that much better, why don't we have them everywhere already?
Yeah, so that's a great question. I'll let you answer it, but I'll let you. So the answer is, the question is kind of, if doing these specialized hardware blocks is such a good idea, what are some of the challenges you face as designers of those blocks, and why aren't they everywhere?
So there's a couple different ways to answer that question. I'll try to take a stab at a couple different ones. The first is, if you look at the past 20 or 30 years of computing, we've been seeing a lot of the improvement just coming from making our traditional CPUs faster and faster. So that's where a lot of the hardware engineer focus has been traditionally. In the past 5 or 10 years, we've been seeing that trend slowing down. And so people are just starting to shift towards considering these more specialized engines. So it's actually a very new phenomenon that's been happening, probably in the last 5 to 10 years, I would say. The other thing that is to be considered here is if we build these very specialized hardware engines, if we put them in a phone that somebody's going to use for 2, 3, 4, 5 years, we also need to make sure that the engine is flexible enough that even some of the algorithms that we aren't thinking about right now, it can run the algorithms that would be developed in 5 years. So it has to be future-proof in a lot of ways. And there's a lot of research that's still being done in how do we realize those different systems. So I guess the answer in a nutshell is it's starting to happen, but it's coming.
So maybe if there's more questions, we can ask them during the demo, but let's give our speakers a round of applause. Thanks everyone for coming, and please check out our flyer if you want to attend future events. Thanks. Sorry.
We have a key inside. Yeah. Something like that. This is, yeah, that's what you want. That was just the basic math.